Today I want to talk a little bit about the simple GUI we've created as a front end for our learning tool. You can find more details about this tool at the link provided here. However, as a summary, what our tool allows you to do is to visualize an error trace through a program which leads to a given assertion violation. The level of abstraction at which this error trace can occur is variable. However, in this case, we're considering it at the level of function calls. So what our tool produces is a finite deterministic automaton which visualizes the sequence of error calls that lead through a program to a given assertion violation. Our aim in producing such an automaton is to provide an accessible and easily readable level of abstraction on these error traces, so that even the most complex programs can be quickly analyzed and summarized. The first example I want to look at and then show how we can analyze this simply and quickly using our tool, especially with the use of our simple GUI, is the following example taken from the software verification competition. What we have here is a reasonably complex piece of code which isn't necessarily intuitive. What we have down here is a single instrumented assertion which we believe to fail. What we want to do is we want to see the sequence of function calls that lead to the violation of this assertion. We can do this very simply and quickly using our tool and using our GUI by first locating the piece of software in memory. Once we have done this, we can simply open this piece of code, and our tool will automatically analyze the different functions available to us. What we can do, therefore, is alter this list. So if you want less functions, for example, if you want to explore or create an automaton which passes through less functions, you can remove them simply by double-clicking, and of course, simply re-add them as necessary. Note that if you try and add a function that does not exist, you will be provided with a warning, as this will ultimately cause the tool to throw an error. Once we have selected which file we want to analyze, we must decide upon two things. These are the word length and the loop bound. Given that we're working with finite state automata, the word length here tells us the longest path that can exist in our automaton. In other words, the longest sequence of functions that can exist on the path to an assertion violation. Evidently, therefore, this value needs to be large enough in order to reach the assertion violation. To help you with this, we provided an automatic analysis tool, which will look at the program and analyze a form of the control flow graph in order to estimate what this minimum value should be in order to produce a reasonable automaton. However, if you wish to specify a word length of your own, you can simply uncheck the automatic box and enter this as you wish. In addition, we also allow you to specify to the model checker which sits behind our tool how we should unwind loops, how many times these loops should be unwound. In many cases, an unwinding of one, especially if your program does not contain any loops, will be sufficient. However, note that the higher this value, the longer the program will take to execute. As I say, in many cases, these default parameters are suitable. We therefore simply hit run, and we will begin to analyze the program and attempt to produce an automaton. Once the program analysis is complete, you'll be presented with the final automaton. This shows the path of function calls which lead to the assertion violation. This automaton will be saved to your hard drive and you can analyze it further. For example, we show you all the function calls which exist on the path to the error. Because we analyze and represent our programs as automata, this provides us with the opportunity to perform standard operations on the representations of programs as automata. For example, we might consider intersecting automata, so we can see which paths exist in one automaton but not in another, and vice versa. Our simple GUI also provides us with the ability to do this. If I press the plus symbol here, I can now specify two files which I can use to do the aforementioned operation of showing which functions exist in one and not the other, and vice versa. If I run this now, what will happen is the tool will first analyze the first program, and then the second, and then perform the intersection, and then the reverse intersection between the two resulting automata. Here is our first automaton, representing the first program. Here is our second automaton, representing the second program. Here we have the intersection between the first program and the second program. And here we have the intersection between the second program and the third program. If we lay these automata out as such, we can see the results of performing our merge operations. Here we have the first program represented as an automaton. Here we have the second program represented as an automaton. And here we've analysed which paths exist in the first automaton but not in the second, which in this case is A, B, C. In the same way, here we have the paths that exist in the second automaton but not in the first, which in this case is the path A, D.